While we're changing speakers, I'll introduce the next presentation. The presentation is from somebody who's well known to this community, worked for a long time in the community, Jean-Marc. It's right, we've just lost the radio mic, I think. Jean-Marc worked in our community for a long time. He's now working with Juniper, has done for how many years now?
Sorry.
2 years. Jean-Marc is going to talk about VPN services that can be delivered either at level 2 or level 3. So I think VPN services are going to become more important. I know I use VPNs all the time. So.
Thank you. Thank you, John. Oop, does it work? Yes? Can you hear me? Okay. Thank you. My talk today will be focused on VPN services, which can be layer 2, layer 3, or Ethernet multi-point to multi-point services. But my intention is really to focus the discussion and the presentation on applications that could be used in the specific context of research education networks. So first, well, why I wanted to, I have submitted this paper to the Terranite conference. This is because mainly 3 reasons. The first is that these type of services are available today in the telecommunication marketplace, if I can say. And they use some components that are common independently of the services you are enabling, layer 3 or layer 2 or VPLS, etc. The second reason is that it's using MPLS, but I would like to try to reposition the role of MPLS here, because using MPLS doesn't mean having MPLS everywhere and changing the way of forwarding packets in the routers. So I will try to address this and explain where is really MPLS here, and you will see that it's much more about BGP enhancement than MPLS forwarding. And the last reason is that I wanted to address the end-to-end issue across multiple domains, because mainly if you attend a conference talking about VPN and so, it will be basically the case studies, which is one domain with customers, enterprise connected to one domain, and the provider providing VPN services between the sites directly connected to it. So I took the different drafts and RFC and just pick up what was interesting, I think, in this context. And before I start, because my introduction is quite long, I would like to say that I'm not going to tell what I believe it's the truth and should be implemented in research education networks. I just want to provide you some components that are not used today. VPN are used in research education, but the end-to-end services are manual today. You just cross-connect some circuits and so. So I would like to bring some new components to start more discussion on that topic, and I will be happy to have this later this week or in next weeks. So, well, you know what's the VPN, and I think that it was already used in research education since a long time, because at layer 2 with ATM PVC, thanks to some projects like James some time ago, 10155 provided an ATM PVC services that with the different national research networks we could establish end-to-end layer 2 VPN. And also the layer 3 VPN based on CP-based tunnels exists since a long time, because this is how you build the M bone and the 6 bone, okay? And we are going to talk about the VPN that you can build over new IP infrastructure and not on a dedicated and separate technology. So just to list the different type of services, layer 3 VPN services, which can be, by the way, IPv4 or IPv6, Typically, we can take the example of a MAN or regional networks that has to support multiple communities. Typically, a MAN that is built with the same, with one fiber, with local authorities, and they have to connect different type of people, of institutions. That can be research education, but also local authorities, enterprise, and so on. And these communities may not have the same right to use external connection, and so some may use the research networks, some may have to use a commercial ISP. So layer 3 VPN services are a good way to segment a common infrastructure to provide separate IP network to support different communities. Layer 2 is much more one example of application could be a European project that require a dedicated infrastructure, and it is how it is used today, like the Atrion project or the 6net project or the data tag project that for some links requires a dedicated circuit but have no dedicated SDH circuits, so they can use a layer 2 point-to-point connections. And I have to mention that when you encapsulate, in this case, a layer 2 frame, it may be the same encapsulation at both ends of the circuits, but it may be a different encapsulation. So you can take one ATM PVC, for example, and on the other end of the circuit have a frame relay circuit or Ethernet VLAN. You will not forward the packet based on the IP address. It will be layer 2 switched, but you can remove the encapsulation at the ingress node and change the encapsulation at the egress node. And the last is the VPLS, which is virtual LAN services, which offers a multi-point connectivity. So in this case, the network will behave like an Ethernet switch in a MAN environment. So in this case, the IP network will provide broadcast mechanism to learn MAC address, and you have the possibility to connect to VPLS instance and get this multi-point connectivity at Ethernet layer. And something that is orthogonal to the services is the end-to-end issues. And why? Because if you take one of the two universities of the maybe 5,000 institution maybe, there is a very low probability that they are connected to the same IP network, right? So VPN end-to-end across multiple domains is a mandatory in the community. On the other way, the advantage is that IP is everywhere. So if we have some techniques that can be used over existing IP infrastructure, if you offer a service to the community, it will be immediately available for the whole community, which is different from building a different infrastructure to provide VPN service. If you build, for example, an optical new network to provide end-to-end point-to-point circuits, you have the issue to provide these services end-to-end because you have to build the infrastructure end-to-end, right? But if you have the possibility to offer layer 2, layer 3 services over an IP infrastructure, the reachability is here. And one comment is that inter-AS issues are specific to research education community, but not unique. Many providers have several autonomous systems in the network due to maybe acquisition. So for any reason, some operators and commercial ISP have multiple IS autonomous systems in the network, and they need to provide to their customers end-to-end VPN as well. So that's the reason maybe why today there is an existing specification for that, which is in the 2547 base, and that's the reason also why it's implemented in router manufacturers. And what was defined in the IETF is working independently of those VPN services that they use, which can be layer 3, layer 2, or VPLS. So that's why we are going to talk a common toolkit independently of the layer 2, layer 3, or the type of VPN service. I will focus my talk to the toolkit that is used for that. Let's forget 1 minute all the VPN story to have a look to a typical, a reference model, really simplified, but just to introduce how it works. Let's consider a backbone. You have several routers. Each router has a loopback address, so you have an addressing space for the internal for the routers. You use an IGP in your network. That may be OSPF or ISAS. BGP to connect the customers, the peering, and you use iBGP internally. That may be a full mesh, or if you use a route reflector, concentrate to 1 or 2 route reflectors. So in this model, which is the standard model to build an IP network, each node has the same reachability information, right? Because at each hop, a router will look in the routing table the corresponding destination IP address and decide where is the next hop. And if we are starting to talk about VPN services, you understand immediately that you have to know much more reachability information, because you have to know where is the next hop to go to one internet destination, but you have to know the destination for a specific VPN corresponding to one customer. So you have much more reachability information, and the only model that would work would be a distributed model that would consist of having the reachability information only when it is required. And this is here when we have this whole concept of MPLS and connected oriented path. This is if you want to build a scalable VPN services, you first must avoid to have any reachability information in the core, so in the P routers here. They must be unaware about all the reachability information. And at the edges, only you will have this information. And to have this model really scalable, you need to have in one P here only reachability information if you have customer interested by this information. Because if you start to distribute all the reachability information, all VPN information everywhere, then you have a scalability issue. So that's why it is required to build some tunnels between the edge routers to avoid any lookup in the core routers. So that's why MPLS exists. Doesn't mean that MPLS is required, because you can use an IP tunnel if you prefer. And today routers can do GRE tunnels at line rate as well. So that's one thing. And if you start to have this reachability information only in some Ps, you need some mechanism to exchange this reachability information, and only when it is required. I had nice animation, but... So what you need is first something between the customer edge and the provider edge, which may be a routing protocol if it's layer 3 VPN, or a layer 2 encapsulation if it's layer 2 VPN. You need a tunnel setup between the Ps. That may be MPLS LSP, or you may use one IP tunnel. And you need some auto-discovery and signaling between the PE, so that each PE will automatically know, announce to the other which reachability information it needs, and exchange labels in order to establish the connectivity at the forwarding plane. And of course, in each PE, you will have several tables. One table would be the internet routing table, maybe if you are an internet provider, and different tables according to each VPN you are supporting in the PE. And the point is that to exchange the VPN information for the auto-discovery and the provisioning of the network, there is one protocol that can be used, which is BGP. And more precisely, multi-protocol BGP, which is already used by all networks, and especially in research education, because you use BGP for V4, for multicast, and also for V6 now. So it's just another extension of BGP to exchange VPN information. And for IPv4, when a packet will arrive in the ingress PE router, the router here, based on the destination IP address and the forwarding table to which the customer belongs, will forward the packet to the egress PE. And the packet will be decapsulated at the egress PE to be sent to the end customer. And with IPv4 services, all customers belonging to one specific IPVPN will be connected as if they were using a dedicated IP network. With IPv6, it's exactly the same. So I think I can skip this slide. With layer 2, this will be exactly the same. The difference is that instead of doing a lookup here of the IP packets, you will just encapsulate what you receive on one logical channel, which can be a frame relay DLCI if it's a POS interface, which may be a VLAN if it's Ethernet, or ATM PVC if it's ATM link. And in this case, the customer will have several point-to-point links connecting the different sites, which may be a full meshed or hub and spoke topology. This is something you can manage by using policy with BGP. Actually, we use the community extensions and policy, import and export policy in the PE to manage the topology. And with IP interworking, this is exactly the same, but you can mix different access technology at each extremity of the network. So you can mix frame relay access with ATM access and provide these point-to-point connections. And with VPLS, the difference is that the Ethernet frame will be switched or flooded if you don't know where to send the packet based on the destination MAC address. And at the egress node, the PE will just look at the source MAC address so that next time he receives the packet back, he will know to which PE to send the packet. So exactly like an Ethernet switch. Flooding is used only if you don't know the MAC address, but you will maintain the MAC address table in order to send the packets to the right PE when the first packets have been exchanged. And in this case, the customer is exactly as if it were connected to the same Ethernet cable link, a shared network with multi-point access. So you can connect a router or you can connect an Ethernet switch to extend the reachability of the Ethernet multi-point connection. So there are actually two labels that are used. One is called the inner label, which is used only for the connectivity between the PE. This is the tunnel. If you don't use MPLS in your core, it will be a GRO tunnel, for example. And the second one, which is the inner label, the first one, the outer label. The inner label is the one that is really used to select the egress ports so according to the VPN information. And this label is exchanged with BGP, which is fundamental because this is how we can extend the VPN services to multiple domains, because BGP is a multi-domain protocol. So if you look at the forwarding plane, the first PE will have two labels. Then you will swap in the core. The penultimate hop will remove the first label, well, the outer label that is used for the tunnel between the PEs. And the last PE will pop the VPN label. OK. So that was just in one domain, just to explain how VPN services can be supported and what is required to be deployed in the infrastructure for that. Let's have a look to the inter-ACE domain, and I will talk about the 2547 bis, which actually has three options, option A, B, and C, and I will have only one slide for option A and B, and focus on option C, which is the real scalable option, and especially if we are considering your context. In option A, first the definition. We use the name of ACE DR, Autonomous System Border Router, the routers that are facing another domain, okay? So here you have two different domains, two different autonomous systems, so it may be one national networks connected to a regional networks, for example. And with the option A of the 2547 bis, it consists of using a BGP, external BGP session between each VPN forwarding table. So, for example, if we have a site here belonging to the VPN blue, it announces with an IGP its route to the PE, which will maintain a specific VPN forwarding table for this VPN. We'll use IBGP to exchange the route with the label corresponding to the VPN to the ISBR. Okay, so this is what happened in the first section. And an eBGP session has to be configured between this VPN forwarding routing table with the corresponding one in the other border router. And then we propagate with the IGP the VPN information to the HP. So you can see that it's quite a complex setup because you need to establish parallel BGP session between each VPN table. And the other restriction is that it works for layer 3 VPN but not layer 2 VPN, because here you have to route the packet. You do a lookup on the IP address. So one enhancement is proposed in option B, which consists of using multi-protocol BGP between the border routers, so that with one single BGP session, we will be able to exchange all VPN tables. So the site will announce its route, it's injected in the VRF. We exchange a label with the other PE, and we use one single multi-protocol eBGP to exchange all IP address with the VPN labels between the two border routers. So the difficulty here is that you need to maintain in the border routers all the VPN information that are common to the two domains. So you still have something that is not doesn't fit well in the scalable model that was designed at the beginning to try to distribute the information and as much as possible. Because in this case, you need to have some routers that have to maintain a lot of VPN information. So that is why we will focus the next part of the presentation only on the option C. Let's take the example of maybe the pan-European network here, two national networks connecting different universities. The idea is the VPN information will be exchanged only by the PE that are connecting customers using the VPN. So only between the extremity of the whole network. Okay? So that means that we need a tunnel between these two PEs, an LSP, so that the forwarding will be based on a label between the two provider edge router. So the idea is between the domains to exchange only internal route of the providers and not VPN information, so that we can establish this LSP from end to end. And we use BGP for that. And then we just have to set up an external multi-protocol BGP session between the two edges to exchange the VPN information. So let's take an example to explain this. We have in each domain a mechanism that can be different from one domain to another domain, but we can use LDP RSVP, well, to set up MPLS, LSP between the edges of each domain. So this is just an internal decision how to implement it and how to manage it. First step. Second step, we exchange PE provider address, so the IP address of the PE routers with IBGP in one domain, and we export it through a direct eBGP session with the other provider. Then we use the same model in this provider. We use IGP to exchange the internal routes between the borders, external BGP, and internal BGP again. So that at the end, this PE will know the destination address of this PE router. But what is new here to the standard BGP is that we use labeled BGP. So in addition to the route, we exchange a label for this route. So we have set up a labeled path between the routers. So we have established a forwarding path, which is the tunnel we are requiring to have this VPN set up between across multiple domains. Having done that, which is the basic setup of the infrastructure, we can configure VPN. So each PE will maintain different VPNs. So for each VPN, there will be a VPN table. So in all my example, I'm taking layer 3 VPN, but it's exactly the same with layer 2 VPN or VPLS. And the two PE have to set up a multi-protocol external BGP so that they can exchange the VPN information and also a label so that we can encapsulate the packet. Okay? So if we look now at the forwarding plane, what we have is the ingress PE will take the IP packet or the layer 2 frame and push 3 labels. The first label here is used only within this domain to reach the 2 border of the autonomous system. No, sorry. This is this label, the outer label. The middle label is used to go through the border routers, so to switch the packets. And the inner label is the one that will be used only by the egress PE to select where to send the packet, which may be a layer 2 frame, as I said, or a layer 3 packet. And you see here how we swap, push, and pop the different labels. So we have 3 levels of labels here, okay? So another idea now. I take the same picture, but instead of asking the domain here in the middle to set up an end-to-end LSP path, I just set up a direct link between the 2 domains that are really maintaining VPN information. So this link may be a dedicated path links, of course, but it may be also a layer 2 point-to-point circuit. So for example, 2 national networks could ask to the pan-European networks to have one dedicated layer 2 circuit, which can be, as it is used for some project today, layer 2 VPN point-to-point links. And then they manage all the VPN without involving the provider in the middle. And by the way, this can be also a GRE tunnel. So we have exactly the same model as in previous slide, but it's even more simplified because in this case, we have the direct eBGP session between the two IS border routers of the two domains that maintain VPN information and provide VPN to their customers. But basically, this is exactly the same. Then we have the end-to-end multi-protocol eBGP. The difference is that at forwarding plane, there will be a direct tunnel between the two ISBR here. Okay. And if I take this with a more complex picture, for example, we have here the pan-European backbone, two national networks, two regional networks or metropolitan networks, and here the universities. We can reuse this model in a recursive way, so it's really hierarchical. The provider here will exchange only internal addresses of the connected providers and networks. These two providers would exchange internal routes of the connected providers, so the metropolitan networks. And the PEs between the will exchange multi-protocol external BGP informations between the PEs that have to maintain the VPN information for the customer. And if I take the ID I presented in previous slides to have shortcut at layer 2, we can have direct connection between the national networks so that we just exchange at BGP level. We exchange directly the internal routes here. Or have the tunnels established between the regional or metropolitan networks directly, which can be a layer 2 circuits or grow tunnels. And if we take this model at the extreme, we can have directly the two universities setting up a tunnel and using exactly the same mechanism to establish a VPN. So that can be having, for example, two VLAN directly connected through a tunnel. So this is really to show you the different concepts, how they can combine, and that you can build really all the different type of service, different architectures, but by using the same components. Don't have to use one specific technology to set up CPE-based VPN or provider-based VPN. And this is the end of the presentation, some concern regarding the scalability. It's really important to understand that the VPN information are only exchanged between the provider edge that require this information, so that have customer connected to it that are using this VPN. Of course, if you consider the whole network, you may have too much BGP session, so you can use route reflectors to simplify the model. Basically, this is exactly as the internet is working today. BGP is a good protocol, it's a proven protocol, and in addition to the internet table, you can use it to exchange VPN information and labels. And as I said in the option C, you can see that there is absolutely no VPN information in the autonomous system border routers, which demonstrate the scalability of the model. And it works independently of the VPN service you provide. So 2 levels of labels to keep the P routers free of all the VPN routing information. This was the first step we achieved in single domain approach. The P routers maintain VPN information only for VPNs whose sites are directly connected to the P router. We can partition the network with BGP route reflectors. So there is absolutely no single component that may there is no single point of failure in the network because the information is really distributed. And there is absolutely no one component that has to maintain all this VPN information. So in summary, I would say that the experience proved that the users in the research education community requires different type of VPN services because we have some example of a deployment of layer 2, of layer 3 VPN. VPLS may be too early because the first implementation is 2 months old only. It can be delivered at a high scale by using a common infrastructure, which is IP, and MPLS in some parts for the domains that want to use MPLS as a forwarding technique. By using a multiple common framework, common toolkit, which is BGP. Common concepts that are used for global internet today, route prefectures, confederation, route targets, etc. And it can be supported, I think that's important, on any type of infrastructure. So those that want to use MPLS in the core and those that don't want to use MPLS in the core. These are all the drafts that were used for this presentation. Thank you for your attention. I would be happy to try to answer to a couple of questions if we have time. I don't know.
Yes, thanks very much. We might have time for 1 or 2 very quick questions. We're running a bit late. Any questions for Jean-Marc? You'll be around your booth if people want to come and talk to you? So in that case, can we thank the speaker for a very excellent presentation? Thank you.